it's okay. In this particular class we are going to talk about the theory of angular momentum in quantum mechanics. Fine. The angular momentum is playing a vital role in both the classical mechanics and as well as the quantum mechanics. So, example, a particle is moving in a particle of mass m moving with velocity v. So, example, particle of mass m moving with velocity v in the direction of x, then it is associated with a linear momentum p is equal to m into v. If the same particle, if it is moving in a circular path of a radius r, x component, this is y component. If this particle with mass m is moving with a circular path, it has actually a two component. One is the velocity parallel to the radius of the particles, the circle, and another one is the cross radial component. Cross radial component, or you can say the tangential this is a circular path, and the velocity of this particle having a two component. One is called a radial component, that is a parallel to radius of the particle moving in circular path, and another one is the perpendicular to the radius of the circle r. Suppose the particle around the origin of the circle with the radius r, then the radial component, if the particle is making a circular path, the particle only having the velocity in cross radial component or the tangential component, and the parallel component v parallel is becoming 0. So, then momentum of the particle is also 0 along the radial component, but the momentum of the particle along the cross radial component having some values. So, this momentum, cross radial momentum p perpendicular to the radius of the circle has written m v perpendicular to the radius. For writing angular momentum of the particle which is moving in a circular motion of radius r, then we can write it L, angular momentum L is equal to the radius of the circular path with the linear momentum in cross radial component, L equal to r into pt, or we can write it r, this linear momentum, cross radial linear momentum m v sin theta, then we can further modify this equation r cross p, or simply we can write it r cross product with momentum is called L, angular momentum is defined that the radius of the particle in a circular motion making a cross product with a linear momentum p in cross radial direction. So L equal to R cross P. This L is nothing but angular momentum and it is along G direction. This is x-axis and y-axis. When the particle is moving in xy plane and the angular momentum is making along G direction, that means the perpendicular to the board. And this angular momentum L, we call it as orbital angular momentum. Orbital angular momentum. In classical mechanics, the rotational kinetic energy ER is directly related with this orbital angular momentum. ER is nothing but the rotational kinetic energy of the particle is making direct relation with the rotational kinetic energy. In case of quantum mechanics, the energy of the moving particle in a circular path is described by Hamiltonian in quantum mechanics. Energy of the particle moving in a circular path moving in a circular path of radius r is described with Hamiltonian H. Is described with Hamiltonian H. This Hamiltonian is nothing but a sum of the kinetic energy and as well as the potential energy. But when the particle is making a circular motion, then the kinetic energy is of mv squared and the moving particle do not have any potential energy, that will be 0. Then further we can modify this equation, H equal to p squared by 2m. Here p is a linear momentum. P is a linear momentum. So make it a equation number. This is 1 and this is 2 and 3. Make it a 4, and from equation 3 the angular momentum, orbital angular momentum L is written as r cross p. If you take it angular momentum square, total angular momentum square L squared, we can write it r cross p multiplied with r cross p. So it will give you r dot r p dot p minus some higher order term, other terms. These other terms will become 0. So we no need to worry about these terms. Now if we reduce this one, r squared p squared is nothing but L square. Angular momentum is written in form of L square. After reducing this one, for getting the linear momentum, p squared is equal to L squared divided by r squared. Equation number 5. If we put the linear momentum In equation 5 with equation number 4, in Hamiltonian H equal to P square is nothing but L square divided by R square 2m. Here m r squared is nothing but moment of inertia I. So H is nothing but L square divided by 2mi. This expression number 6 is clearly telling us that the angular momentum of the quantum particles also associated with the Hamiltonian. Here the angular momentum of the classical particle is associated with the rotational energy of the particle. Here angular momentum of the quantum particle is also associated with the Hamiltonian of the system of particle in quantum mechanics. So it's clear that angular momentum of the particle in quantum mechanics is playing a important role to understand the behavior of wave function in quantum mechanics, such as motion of electron in atom and as well as the nucleons in nucleus under rotational symmetry. In general, the equation for orbital angular momentum L vector is written that the radius of the circle of the moving particle R makes vector product with the momentum, linear momentum of that particular particle. L equal to R cross P. And here R is the position vector and P is the momentum, linear momentum of that corresponding particle. So if we are writing R vector is nothing but x I y j g k. Here I, j, k are unit vectors along x, y, z direction respectively. And linear momentum, we can write it p x I vector, p y j vector, p z k vector. And writing for total angular momentum L is also similar to the linear momentum Lxi, Lyj, Lzk. By using all these equations, the L total angular momentum can be written in vector form, matrix form I, j, k, and the value of position vector is x, y, z, and the linear momentum is nothing but px, py, pz. If you simplify this expression, L is nothing but I y with pz minus py with z. Bracket minus z vector x with pz minus px with z plus k vector x with py minus px with y. Equation number 9, make it. And if you compare the equation number 9 with this angular momentum, total angular momentum in equation number 8. If you compare these two, then Lx can be written ypz minus pyz, and Ly can be written, there is one negative sign is also there, so if we put inside to this expression, then pxz minus xpz. Ly and Lz is written xpy minus pxy. This can be written zpx minus pzx, there is no problem, and this is equation number 10. In quantum mechanics, every observable is associated with a operator. That operator we call it a Hermitian operator, and in particularly angular momentum in quantum mechanics, the orbital angular momentum is also a observable, and that is also associated with angular momentum operator, which is called L vector cap. This is operator. So if we write it in the operator form of this equation, then Lx operator in vector I plus Ly operator in j vector, Lz operator in k vector. But for solving the one-dimensional Schrodinger equation of the free particle, the wave function psi of x comma t is written exponential I by h cross p times position minus energy time t. Make it number 11, 12. If we take the first order differentiation with respect to position of this expression number 12, dou divided by dou x is equal to here I p divided by h cross, then e power of I divided by h cross px minus et. So simply we can write it dou divided by dou x equal to I p divided by h cross. So psi of x t, x comma t, and this is also psi of x comma t again. So gets cancelled on both sides of this expression. Then dou divided by dou x is equal to I p divided by h cross is remaining term. From this expression we can get it the linear momentum p operator equal to h cross divided by I dou divided by dou x. Or we can further modify this expression because I is in denominator, imaginary part, then if we take it in the numerator minus I h cross dou divided by dou x. This is momentum operator along x direction. This expression number, make it 13. So similarly we can also write it py operator also minus I h cross dou divided by dou y, and momentum operator in g direction, linear momentum operator in g direction also can be written then. If we are putting these values px, py, pz in equation number 10, so we can write it all the orbital angular momentum in quantum mechanics in the form of operator. So Lx operator is nothing but y pz, pz is here I h cross dou divided by dou z minus py, py is also I h cross dou divided by dou y z. Further we can simplify this expression. Here one I is there, these two if you multiply it will become a positive sign, then I h cross dou divided by dou y z minus I h cross dou divided by dou z, then y you can write like this. So further I h cross you can put it outside, or from here also we can write it. Minus I h cross, you take it minus I h cross outside y dou divided by dou z, now negative sign with z dou divided by dou y. Similarly, the orbital angular momentum operator along y component also can be written minus I h cross z dou divided by dou x minus x dou divided by dou z, and Lz operator minus I h cross. So z is here, then x dou divided by dou y minus y dou divided by dou x. This you make it equation number 14. So we can replace this equation L equal to the determinant of I, j, k, x, y is at position vector and then momentum vector by using the expression number 13. So L equal to I, j, k. So here this is x, y, z, and px, py, pz is here. Px equal to so I am taking minus I h cross outside, and then dou divided by dou x, dou divided by dou y, dou divided by dou z. Further, this expression minus I h cross, so this one represent position vector R making vector product with del. Here the del operator is nothing but I dou divided by dou x, z dou divided by dou y, k dou divided by dou z. It's nothing but del operator. Fine. This is actually the angular momentum of the particle moving in a circular path. Okay, now let me discuss something about the angular momentum algebra. According to commutator algebra, the position of the particle and momentum of the particle do not commute with each other. So more precisely we can write this expression, position of the particle in x direction and the momentum of the particle also in the same component do not commute with each other. That means the position of the particle and momentum of the particle along x direction cannot be determined precisely. According to uncertainty principle, x comma px commutation will give you I h cross question number 15. But can be measured position of the particle in one component and momentum of the particle in another component, say example py, can be measured precisely. Similarly, we can also write it, the position of the particle in x direction and y direction is equal to zero. Position of the particle in x component and y component can be measured precisely. Any of two components, say x component, y component or y z component or z x component can be measured precisely. Similarly, the momentum of the particle in x component as well as y component or in any two component, momentum of the particle in any two component can be measured simultaneously. Similarly, the position of the particle in one component and momentum of the particle in another component y with px z with p x x with py, so x with pz, y with pz, z with py gives 0. Based on these arguments, particularly based on this argument, momentum of the particle in any two different component will commute with each other, or otherwise can we say momentum of the particle in x component and as well as in the y component can be measured precisely. This is nothing but a linear momentum, px, py, pz, or the linear momentum of the particle in x, y, z directions. But based on this argument, can we write the angular momentum of the particle in different component be measured precisely or not. Say example Lx, Ly. If Lx commute with Ly, what is the answer? As per this argument, we are expecting 0. However, let's calculate commutation of Lx with Ly. So Lx and Ly, we have already written Ly operator. This all are operator. So this Ly operator values are Ez Px operator minus x Pz operator. So how to write this one? So Lx first commute with this component, then further again Ls commute with this component, second component. So Lx comma Ez Px negative sign, Lx Pz. Okay, let's write the complete expression. So Lx Ez Px minus Ez Px Lx. Here already one negative sign is there outside, so you use it the same. Lx xpz, then one negative sign will come. If you multiply with this negative sign, it will become a positive sign. So xpz and Lx. Now you put the value of Lx here, Lx operator. So the value of Lx operator ypz minus ezpy. So multiplied with zpx. So minus gpx ypz minus ezpy then minus ypz minus ezpy making with xpz, then plus xpz Lx again y pz operator minus ezpy operator. Now we multiply y p z operator z p x operator minus zpy zpx, this second term. Again make it minus sign here, z px operator y pz operator. So negative sign, if you put it, then it will be positive sign. Z px operator z py operator. Then here again another 4 more terms will be coming. So minus y pz operator multiplied with x pz operator. So here one negative sign is there, another one negative sign. So it will be plus sign z py operator x pz operator. Then here x pz operator y pz operator minus x pz operator z py operator. In this particular term, so if it is zz, this is nothing but a self commutation. So this term will become 0. Similarly, this term also will be 0. This 2 term will be 0 first. So by considering first term with the third term, y pz zpx minus the third term zpx y pz. Here if you look this term pz do not commute. That means pz if you take it, it do not actually commute. But if you look here, any of the term, if you make it any combination zpx, zpy or pxy, pxpz, whatever the combination, so this will actually commute. So here we cannot interchange the p z, But here we can interchange any of this term in as per our requirement. So that is equal to y pz cap z px cap minus y z px pz. We are writing in this way. Then taking out y pz is at px minus z px pz. Further we can modify this expression y pz is at z pz px. Similarly, by considering this term, sixth term, and as well as the last term 8, because other terms will become 0 because pz commute self commutation, so this will become 0 again, and this term also will become 0. So by considering the term 6 and 8, eighth term z py x pz minus x pz z py. Again, if we look here in this expression, z can commute with py, z can commute with x, z can commute with pz. So x also can commute with z, py and pz. So we can actually rearrange the position of z, py, x, pz as we required. So for that I am rewriting this expression x z py pz minus, here we cannot actually reposition because pz do not commute with z. So x pz a py. Then if we are taking x outside, z py pz minus pz z py. Again here Py can be taken out. X Z Py minus Pz Z Py. If we are adding these two terms, we will get the commutation of Lx with Ly. Y with Pz cap Z minus Z Pz cap Px cap plus X of Z Py cap minus Pz Z Py cap. So this, we can actually rewrite this formula again. Y Pz minus Z Pz as per our convenient. So take it a negative sign outside, then X Pz minus this is Pz. So Pz Py cap. So this term is actually common here, so we can take it outside. Y Px minus X Py Pz minus Z Pz can be simplified. So further, this term is nothing but I H cross commutation of these two terms. That means Pz commute with Ez will give you I H cross. That means the momentum of the particle minus I H cross. So commutation of Pz with Ez will give you minus I H cross, and this value is associated with the angular momentum operator in G direction, and this is I H cross. So it will give you I H cross Lz. Lx, Ly. If these angular momentum operator commute, the results leads to a third angular momentum. If rotation is in xy plane, the result will come in z direction. Angular momentum result will be in the z direction. Similarly, we can also write for other commutation, other combination of commutation. For example, Lx, Ly, Ly, Lz. The commutation of this angular momentum in y and z component gives as I h cross L x, and Lz commute with Lx gives I h cross L y. In general, what are we understanding from these relations means it cannot possible to measure the angular momentum in two different components simultaneously. The way which we are measuring a linear momentum in two different components simultaneously is possible. Px, Py is possible. Linear momentum. Possible for linear momentum. But for angular momentum, measuring in two different components simultaneously is not possible. So in general we can write so example, angular momentum in A component commute with the angular momentum of B component will give I h cross the angular momentum in a third component Lc here with one coefficient is called epsilon ABC is called Levi-Civita symbol. The value of epsilon ABC is 0 in case A is equal to B or B is equal to C or C equal to A, and the value of this constant epsilon ABC will be 1 for all cyclic permutation. Example, A, B, C, that means X, Y, Z, comma, Y, Z, X, comma, Z, X, Y. It's called a cyclic permutation. Then the value of epsilon ABC is 1, and if non-cyclic permutation for this ABC is nothing but X, Z, Y, Y, X, Z, Z, Y, X, this will be minus 1. So non-cyclic permutation. non-cyclic permutations. Fine. That means if L x L Z, if commutation of L x L Z, this will give you minus I h cross L y. Example, if commutation of this non-cyclic terms x Lx commute with Lz will give you minus I h cross Ly. It's a non-cyclic permutation here. Fine. Let's move to total angular momentum operator. So, in quantum mechanics, the total angular momentum operator is represented with L square. So, example, if you take it, operator L is Lxi Lyj Lzk, then L square is nothing but Lx square Ly square Lz square. We have set of a orbital angular momentum operator, a set of orbital angular momentum operator that is nothing but L square L Lx Ly Lz. So, we had to check it whether the total angular momentum L square commute with the Lx, Ly, Lz. So, what is the answer for if the total angular momentum L square commute with the angular momentum of the particular component, say example Lx, Ly or Lz. So, we will consider first L Z or Lx. That means we are going to check it whether the total angular momentum of the system and angular momentum of the particular component can be measured simultaneously or not. So, in case of L square, we have this value L x square, L y square, L z square, comma, so Lx. So, if it is commute L x squared with Lx plus L y squared commute with Lx plus L z squared commute with Lx. The total orbital angular momentum in x component commute with the angular momentum in x component. what will be the result? So certainly we can actually write it for this particular expression Lx Lx comma Lx. So it is a self commutation. Lx commute with Lx will be 0. Then directly we can write it. This is 0 and plus the total orbital angular momentum of y component commute with the orbital angular momentum of x component. And as well, the total orbital angular momentum of g component commute with the x component. What will be the result? For taking only this particular term, second term, Ly squared Lx can be written, this particular term only I am taking here. So Ly Lx. So this Ly commute with Lx by keeping Ly. So by keeping this Ly, second Ly commute with Lx. Some of our earlier relation Lx Ly is nothing but I h cross Lz, Ly L Z, I h cross L x, Lz Lx, I h cross Ly. If you interchange these two positions, say example here, if I am writing Ly Lx, if I am changing the order, then we have to introduce a negative sign here, this negative sign. If you are interchanging these two positions, then you have to introduce a negative sign because order, the cyclic order is becoming a non-cyclic order, then you have to introduce a negative sign. If you look here, this expression, so Ly commute with Lx, but we have Lx commute with Ly. So if we make it in this order, then we have to introduce a negative sign minus I h cross L z, then Ly already is in the expression. Similarly, again, so Ly is there and Ly Lx, again we had to write I h cross Ly Lz. So you keep it this expression here and then taking the second term of this expression here, Lz square Lx is nothing but Lz comma Lx. Then further can be extended this one by keeping this Lz, second Lz, first Lz commute with Lx. So Lz commute with Lx plus, by keeping first Lz, second Lz commute with Lx. All are operator, so don't forget to put operator symbol. All are Hermitian operator, keep in mind. Fine. Now if you look this expression again, the order Lz Lx is fine. So this is in cyclic order. So we can write it IH cross Ly Lz plus, refer it to this one, Lz, again IH cross is there, you put outside, Lz Lx Ly. Adding these two term here, L square Lx is nothing but minus I H cross Lz Ly, this term, again minus I H cross Ly Lz, then you add it to this term plus I H cross Ly Lz plus I H cross Lz Ly. So Lz Ly with the positive sign, Lz Ly is negative sign, gets cancelled. Again if you look, these two term also will get cancelled. The final result is 0. So what we are understanding from this, can be measured the total angular momentum of the system L and the angular momentum of the particular component either x or y or z can be measured simultaneously. Example, L square Lx 0 can be measured is equal to L square Ly also equal to L square Lz. So total angular momentum of the system and angular momentum of any one of the component either x or y or z can be measured simultaneously. So in general we can write it L square Li here the is equal to 0 and I is nothing but x comma y comma z, anything. Okay, in summary, the component of L, either x, y, z do not commute with the total angular momentum L. So In summary, so the component of angular momentum do not commute with each other. Example, Lx, Ly, Ly, Lz, Lz, Lx. So it do not commute with each other. So it is not possible to obtain the eigenvalue or eigenvector for all of these three components Lx, Ly, Lz. If we want to find out the eigenvalue or eigenvector of these three values Lx, Ly, Lz, by using this method it is not possible to measure it because it do not commute with each other. The second argument is that L square, the total angular momentum L square can commute with any of the component of angular momentum L square can commute with any of the angular momentum so we can say there is a common eigenvalue for this, common eigenvalue or common eigenvector of or eigenvector for L squared and Li. But here no common value, no common eigenvalue or eigenvector. So next target is to find out the eigenvalue and eigenvector of L squared and L in a particular component. So find out the eigen values of angular momentum operator Lz cap and L squared. For finding out this eigenvalue or eigenvector of the total angular momentum L squared and the angular momentum with a particular component, say example Lz, we have to introduce a two non-Hermitian operator. These non-Hermitian operator are called L plus and L minus. These two operator L plus is nothing but Lx plus Ily and Lx minus Ily, its complex conjugate with each other. Example, this is Lx component and Ly component, and this point is nothing but L plus operator Lx plus I Ly. This is a real axis, this is imaginary axis if we take it. Then if our raising operator L plus is nothing but the raising operator and L minus is nothing but the lowering operator, so the angular momentum is in quantum mechanics is a quantized value. So L plus is actually, if we are moving from x to y, then we call it as a raising operator. Then if it is coming from Ly to Lz, then lowering operator, or we can call it as lowering operator if we are moving in this direction, Lx to minus Ly. We call it a lowering operator. So this is L minus is nothing but Lx minus I Ly, call it. Because it's actually raising and lowering the eigenvalues from that the normal value of the angular momentum. From this we can manipulate the value of Hermitian operator Lx and Ly So Lx is actually here. If we add these two terms, then we will get it 2Lx is nothing but L plus L minus. And similarly, if we are subtracting these two terms, 2I, I am subtracting this term with this term. So L plus minus L is L minus. From here, we can write it Lx is nothing but 1 over 2 L plus L minus. Here we can write it Ly 1 over 2I L plus minus L minus. This is the relationship between the Hermitian operator and non-Hermitian operators. Also in harmonic oscillator, we call it as this ladder operator. You might be studied already in harmonic oscillator about the raising and lowering operator, and which are collectively known as ladder operator. Okay, now let me check it. The angular momentum operator Lz in Z component commute with the raising operator and lowering operator. So first let's check it. Lz commute with raising operator or not. So we can write it Lz as such, and L plus we have this value Lx plus I Ly this is nothing but further Lz commute with Lx plus I can be taken outside, again Lz Ly commute in such a way. Then we had already studied, so Z and X, this is a cyclic commutation, Z followed by X, so it will give you I H cross L Y. But if you look at here, this is actually a non-cyclic, Z followed by Y, then it will be the negative sign here, minus I H cross L X. So if you take it, already one I is also there here, then put it that also. So I squared will be the negative sign, so it will give you here I H cross Ly plus H cross Lx. Then this term can be written with the common H cross Lx plus I Ly. Again this term is nothing but H cross Lx plus I Ly is nothing but L plus, so L plus can be written here. So similarly, Lz with lowering operator, if commute the angular momentum of the particular component z direction, commute with the lowering operator, then Lz comma Lx minus I Ly again Lz Lx commute minus I Lz Ly. So Z followed by X is the cyclic commutation. So I H cross Ly, one I already there, and if you look at this is a non-cyclic, so I H cross so one negative sign we have to add it here, Lx. Okay, this is plus sign. Then one I is here, then Lz Ly will become minus I H cross Lx. So this I squared will give you minus 1, already one negative sign is there, then this will become positive sign only. Similarly, if you look at here, then I H cross Ly minus I squared, then this will be the positive quantity, then H cross Lx. Again, if you take out H cross outside, minus H cross outside, then Lx minus I H cross I Ly. Minus H cross Lx, so minus into minus plus I H cross Ly we are getting here, then minus H cross Lx minus I Ly is nothing but L minus, so write it L minus. by combining we can write it L is at L plus minus is nothing but plus minus H cross L plus minus. So the commutation of LZ with L plus and L minus will give you plus or minus 1 as an eigenvalue. These are all the eigenvalues. Fine. Similarly, Lx with L plus. So we can write it Lx, and L plus is nothing but Lx plus ILy, we know very well. If it is commute, then Lx, so self commutation, it will become 0, I, Lx, so Ly. So this answer is 0 plus I, Lx, Ly. It's a proper cyclic permutation, so we can write it I H cross Lz, or the answer will be minus H cross Lz. I squared will give you minus 1, and Lx commute with L minus, again Lx minus ILy, then again self commutation, Lx will become 0 minus I Lx Ly, then answer will be 0. So here minus I, this will be xy, so no problem, I H cross L Z. Then answer will be plus I square minus 1, already one negative sign is there, so it will become plus sign Lz. Then by combiningly we can write it Lx L plus minus is nothing but minus plus H cross Lz. Similarly, one can also write Ly with L plus is nothing but Ly comma Lx plus ILy then Ly Lx plus I Ly. So here self commutation is coming, so then this will become 0. Here Ly Lx, so it's a non-cyclic commutation, then minus I H cross Lz. Again, if we verify Ly with L minus commutation, then Ly Lx minus ILy then Ly Lx, again it is a non-cyclic permutation or the commutation, minus I Lx Ly. So again this will become 0, self commutation, and here again minus I h cross Lz. So there is no change of sign like how Lx is commuting with the raising and lowering operator. In case of Ly, if it is commute with the raising and lowering operator, there are no sign changes. So we can write it Ly L plus or minus is nothing but minus I h cross Lz only. Okay. Suppose if it is commuting the raising and lowering operator, only these ladder operators are commuting with each other, what will be the answer? So take it L plus and L minus, we know that Lx minus I Ly, then we can extend to this one L plus Lx minus I L plus Ly. So the L plus commute with Lx, again we have to write it Lx plus I Ly, Lx commutation minus I Lx plus I Ly commutation. Then so Lx with Lx self commutation will be 0, then I Ly Lx commutation is possible. Here again one negative sign is there, I am keeping I. So Lx with Ly is possible, and this will give you self commutation is 0. So if you look at here, so again this is a non-cyclic, then I Ly Lx, so minus I h cross Lz, then minus I, so xy is a cyclic permutation, so Lz, I h cross Lz. Already one I is there, then I h cross Lz. Then if we are simplifying, I square minus 1, one negative sign is there, so h cross Lz, then plus I square, again here another Lz, so 2 h cross Lz will be there. Similarly, we can also check it L minus lowering operator, if it is commute, so L plus L minus, so L minus L plus, lowering operator commute with the raising operator, then answer will be minus 2 h cross Lz. The final result is on z direction only. Then L, So for determining L squared operator with the raising and lowering operator. L squared operator with raising and lowering operator commutation. What will be the answer? Let's check it. L squared with the raising operator Lx plus I Ly, and no problem, you keep it L squared, then Lx plus I L squared comma Ly. So as we already discussed, the total angular momentum operator L squared and the angular momentum of the particular component, say x or y, can be measured simultaneously. Then this term will be 0 plus this term will be also 0. Then if total angular momentum commute with either raising operator or the lowering operator, it will be 0 only. The physical meaning of this expression is that we can measure it, the total angular momentum, and as well as the raising operator and the lowering operator simultaneously. Now I would like to summarize so far what we discussed here. The component of L do not commute. That means LA, LB, if you take it, the angular momentum in A component and as well as the B component, then the final result IH cross ABC LC. And second, the operator L plus raising operators and L minus do not commute. That means L plus and L minus cannot be measured simultaneously. And the third point, the total angular momentum L and operator and L plus and L minus operator do not commute. So, for example, angular momentum in z direction, we are taking L plus minus, so it will be plus or minus h cross Lz, so L plus minus. Similarly, if you take it Lx, L plus minus, then answer will be minus plus h cross Lz. If you take it, the component y commute with the raising and lowering operator, the answer will be minus IH cross Lz. Finally, the component of L angular momentum in particular component L I, here I equal to x comma y comma z, and L square total angular momentum, it's commute with each other. That means L square Lx equal to L square Ly is equal to L square Lz is equal to 0. And the total angular momentum L square, if it commute with the raising and lowering operator, it will be 0. So next class we will discuss the angular momentum quantum number and its relevant physics.